Welcome to today's webinar, Analyzing Functional Data. We are going to have one of our statistical scientists, Ross Matusalem, give the presentation. He's one of our academic ambassadors. And as we've shared with many of you who attend our webinars, we do have these webinars and of course some recorded webinars on the website, but we're here to support you. So we will be able to do a custom webinar for your class, for you and your colleagues, or just if you want to hop on and have a Q&A session or see some specific tools of JMP, that's what we do. We're here to support you. So don't think that attending these webinars or looking at our resources on our website are the only way. Please reach out to us. You see the email address on the screen, academic@jmp.com, and we'd be happy to run a custom presentation session for you. Ross is going to show you this either at the beginning or the end. He's going to point you to all the teaching and learning resources that we have to support you in using JMP in your teaching. And with that, Ross, I think I'm going to hand it over to you to begin the webinar. If you have any questions while the webinar is going on, please type them into the Q&A session, and I'll either answer them along the way or we will wait until the end. This is a topic I'm not tremendously familiar with, so I'm excited to learn from Ross. So I might have to wait until the end to answer those questions. Also, we're always looking for ideas on what kind of webinars or topics that folks would like to see. So if you could go into the chat box and type in any suggestions you have for webinars you would like to see. This is the last webinar of our spring semester, but we'll be planning our next webinar series. So if you have any you want to see, please go into the chat and type them in. We'd be happy to create some webinars based upon your input. Okay, Ross, with that, I'll hand it over to you.
All right, thanks, Kevin. And thanks everybody for attending today's webinar on functional data. I'm just gonna turn my camera on real fast just to say hi to everybody. Appreciate you coming to learn about this pretty powerful technique for a type of data that I think is certainly ubiquitous in many domains to the point where maybe sometimes we're using or analyzing it and not even knowing it. All right, so enough for my camera and saying hello. Just wanted to show my face a little bit. Let's dive in. And normally in these webinars, if you are used to them, you know that we get straight over to a JMP demo. I actually, because this is a topic that I think is somewhat unfamiliar to a number of people, and certainly by looking at the poll results, I think might even be brand new to over a third of the people here. I actually want to start with just a primer about what functional data is and how we might analyze it in different ways. So functional data is any kind of data where one continuous measure is, I'll say, unfolding across another. So take, for example, sensor data. So imagine that you have some sensors that are continuously recording some kind of continuous value as it unfolds over time. So I have an example here from a fermentation process in a biomedical setting where we're monitoring the pH inside the fermentation tank over time. And you can see in 5 different fermentation batches, we actually have different profiles of this functional or curve data. So for example, batch number 1 here, the pH starts high, drops, and then comes back up before stabilizing. Whereas in batch number 4, in this light blue, we see kind of the opposite. It starts low, rises, and then stabilizes. So this functional data has certain shapes or features to it that, as we're going to talk about throughout, it might be particularly important to us. Another prominent example is spectral data. So here I actually have some near-infrared spectroscopy data on gasoline. So instead of time on the x-axis, we have wavelength in nanometers, then we have reflectance of light at the various wavelengths on the y. And actually, because this is gasoline, I've colored these by the octane rating of the gasoline to see maybe how the shape of the spectra actually relates to the gasoline's octane. This is just another example of one continuous measure, reflectance unfolding across another wavelength. And we'll take a look at these data as we go through today. Another prominent example, time series data. So with all the talk of inflation and cost of living, I was actually just kind of for fun, honestly, looking at some consumer price index data the other day, and made this quick graph of how we can see that throughout time, we see various rise and fall in the CPI in various categories. So for example, we can see that food and beverage costs were rising really, really slowly until maybe about 1975 or so, and then started to exhibit a steeper incline. We can see a similar pattern here for medical expenses. Maybe this initial rise was a little higher, but certainly a much steeper increase afterwards. So we have just a few different examples here of one continuous measure unfolding across another, but they all are common in that the unit of measurement, the thing that we might be interested in, isn't a single point or a single value. It's the curve that we're looking at, and the features of the curve, what those might tell us about, or what they might mean, and also maybe how they might relate to other measures that we care about. Analyzing data like this, analyzing functional or curve data, can present a specific challenge, and that really is how to best identify and quantify important curve features. So we're going to start with a admittedly generic example when we actually get into JMP. But here's a plot of the data that we're going to be working with. So we just have a continuous X and a continuous Y, and we can see with these, the points are some data we observed, and the red lines are some functional curves that we fit to those data. And you can, just for the sake of your own understanding, map this to whatever you might, want, or whatever data is relevant to your domain. Maybe, this is concentration over time in runs of a chemical reaction, or maybe it's the density of a species or of plant or animal over time across different study sites, or maybe this is different sectors of the economy having consumer sentiment changing over time. Whatever helps you kind of think about functional data in a way that's intuitive to you. So when we have data like this, we might want to capture the differences in the curve shapes that we see here in order to figure out maybe how and why they differ. Now, how do we do that? Well, traditionally, and this is actually something that I was trained in, I come from cognitive science and worked in a cognitive electrophysiology lab, so EEG, brain waves, and we would get curves, fluctuations of voltage over time, and then need to characterize the shapes of these curves in some way. And so we would do things like take the mean or the minimum or maximum or range in some time window. And we could do that here. Maybe we take the minimum value and use that as some kind of summary of these different curves. And so, here's the minimum value of curve 1, and that's much lower than that of curve 2 and maybe curve 9. And so that summarizes something about the curve, but it's certainly throwing away all the information of everything leading up to that point. We might do something a little more sophisticated. We might try to figure out what the time or the X value is of the inflection point. Maybe we can even try to, compute a derivative and figure out where that derivative crosses some threshold. So you could imagine, here we have an inflection point at maybe 10. Here, the inflection point looks like maybe it's at, 6 or 7. Here it's even earlier, let's say maybe 5. Well, we could summarize these curves that way. Or maybe we'd look at, say, the slope of the decrease in these curves. And you can see that as they start to drop off, the slopes are highly variable across all of these. Some are very steep, others are relatively shallow. Now, these are just a few of the various ways we might try to create numerical summaries to capture the differences in curve shape. And they're particularly imperfect in that they throw away information. I mean, imagine a situation in which we want to do some simple analysis relating curve shape to some other variable we care about. And so here I just have an example. This is just a simple linear regression equation. So y is some variable we care about, and we want to say that it's related to curve shape through some equation. Now we know that we need to put some value into that equation, but which one should we use of all these that we said? Or maybe even some additional potential measures of these curves that we haven't even considered. This right here figuring out which measures to use in order to perform certain analyses is actually a really complex and fraught problem that often brings with it a lot of assumptions about what parts of a curve are and aren't important. And no matter how, accurate we might be in taking our best guess of these appropriate summaries, the problem with any of these is that ultimately using these, what I'll call landmarks, like the mean, the minimum, and the maximum, they throw away information. No matter how many we use, we're never going to actually be able to use all of the data to try to uncover the different ways in which curves vary, and then be able to use that in an analysis in any meaningful sense. And so what can we do instead of using these landmarks? Well, JMP's Functional Data Explorer, it uses a different technique from the general domain of functional data analysis that allows us to explore curve shapes and extract curve features using all of the data that we have. So let's consider these same curves that we were looking at before. What Functional Data Explorer does is it represents each curve according to a few what we'll call shape components. So let's imagine that all of those red curves on the left can be represented as some average. So this is just the average curve across all of them, plus or minus some amount of 3 what we'll call shape features. In the statistical terminology, it's actually Eigen Functions. So let's take a look at just this first curve. Oop, wrong button. This first curve feature here. So this is showing us that this element of each curve, really towards the second half, seems to vary significantly. Really, that is related to, let's say, the drop-off at this point around 7 or 8. And so we're talking about maybe the degree to which a drop-off occurs right here at the shoulder point for each of these. And so we have a couple other shape features as well. So here we can see one that seems to capture both maybe an initial rise or hump before the drop off, and then particularly steep fall. And here's one that also captures that hump, but then maybe a component that actually starts to turn up like a little tail at the end, which we can actually see maybe right down here, for example. So what we can do is actually model all of our curves using these 3 shape components. And as you can see with this animated profiler I have down here, you can assign actual numerical values or scores to each of these shape components. So where it says FPC 1, 2, and 3. So here we have a negative score and now a positive score for FPC 1. We can see how that actually changes the shape of these curves. So this is a particularly powerful way to both explore and identify the primary ways in which curve shapes differ, and then also be able to extract numerical values that correspond to these complex variations in curve shape that we can use for other analyses. The real benefit, as we're going to see through a few examples of this approach, is that we can use all of our data to identify primary curve features, and that's where we're going to start. We can capture complex curve shapes in numerical values. So we're not capturing, the peak of the curve or the slope of the curve. We're capturing much more complex shape features, but still doing so in simple numerical form that can be used in other analyses. And then we're actually going to see how we conduct these analyses between curve shapes and other variables by using these values that we extract. Now, I'm going to try to stay relatively high level here as far as exactly how functional data analysis works. I don't want to get too deep into the math. I'm actually not the best person to do that anyways. Instead, we're going to focus mostly on JMP's tool, Functional Data Explorer, and how to use it effectively through several examples. So I do want to say that if you want to learn more about this particular topic, here is a reference that we would recommend, Ramsey and Silverman's 2005 book, Functional Data Analysis. JMP's Functional Data Explorer draws extensively on the methods that are discussed in this book. So do have a look if you'd like to go a little deeper on how all of this works. So with that, let's actually see how to do just a basic functional data analysis through that example that we were just looking at in the slides here.
Hey, Ross,
Yes.
before you jump into the example, a question came up. Is there any requirements on the sample size needed to use this technique?
As we're going to discuss, I mean, there aren't any strong requirements, except that you need to essentially have a sample size that will allow you to accurately capture the features of the curve that are important to you. So you could simply take 2 measurements, and that could be a function, right? It would be a simple one, a simple line connecting the 2 points. And if those lines are meaningful to you, then maybe you could capture that. But I mean, in reality, you want to sample at some kind of rate over that X or over that continuous domain that is going to accurately capture curve shape. And that's going to vary quite widely from domain to domain. So this is a place where your own domain expertise is going to be pretty important. Were there any other questions that came through, Kevin?
That is it so far.
Okay. All right, so let's take a look at just that example from the slides. We saw I had some curves, I had 3 shape components that I extracted. How do you do that? So we're gonna use these data. We're gonna actually, before I said, choose your own adventure, map whatever knowledge you want to those data, we're gonna imagine that they're from a biochemical reaction where we're measuring the concentration. So that's what Y is here over time across numerous batches or numerous runs of this reaction here. So how would I, if we just take a look at those data, which we saw before, here it is in slightly different graphical format, how would I use functional data analysis to be able to capture the primary ways in which these curve shapes differ? So I'm going to use Functional Data Explorer. And again, as I've mentioned a couple times, this is a feature that's exclusive to JMP Pro. It lives under the specialized modeling menu. So I will tell it that my Y or output or my measure is this Y or concentration variable. My X or my input, or you'll hear it referred to as my domain, is time. And I will tell Functional Data Explorer which row corresponds to each of the batches, as we see on the left there. We're going to get into the mechanics of using the Functional Data Explorer tool right now, or in a moment. So right now, I'm not going to talk about everything that you're seeing here. We're just going to cut straight to the good stuff. What we've done is we've imported all of our data. So this graph just represents literally every data point that we have overlaid on a simple graph. And down below, we have all of the individual batches worth of data. What I need to do is fit some functional curves to my data so that I can then extract the shape features from those curves. So step 1, we're going to just fit some curves to our data. You can see this is now the plot we were looking at in the slides. I've actually fit a model. These are flexible models. They're called spline models, or it's a basis function expansion model. You can see those in the red lines. We can see if we actually zoom in on any of these, they're not passing directly through the points. We're not just simply connecting the dots. We've actually fit a model, but it seems to fit the data pretty well. And now below, we have extracted our 3 shape components here using a technique known as functional principal components analysis. So if you know Pca, you can go ahead and bring that knowledge along with you. If you don't know Pca, it's basically a way of determining the primary direction of variability in data. It's often used as a dimension reduction technique. So we performed Pca on our functions, and it's told us that these are the 3 most prominent ways in which our functions differ all around this average here. So let me try to unpack that a little bit for you, make this a little bit more intuitive. So down here, I have a plot where we have 1 dot per batch, and I have each batch's score on these different shape features plotted. So let's just hover and grab batch 14. All right, so here is batch 14. That is what the result that we got on that batch actually looks like. And we can see that it says it has a component 1 score of 0.5 and a component 2 score of -0.1. So I can actually adjust in this profiler here those scores. And then on the left where it says time, we can actually see what the model would produce as the curve given those scores. So you can see as I increase this score, it actually creates a much more dramatic drop off. And as I decrease it, it creates a more gradual drop off that doesn't go quite as far. So let's go ahead and just put batch 14's score in, and that was 0.5. And then over for component 2, it had a score of -0.1. So maybe I'll enter that. And we'll just skip component 3 for now. As you can see, with just even these 2 values right here, 0.5 and -0.1, we've essentially been able to recreate the functional curve that we observed in batch 14. So we have complex curve shape now summarized in just these 2 values. Let's take a look at a different batch altogether. So let's go batch 2. So batch 2 looks a fair bit different than we just saw in 14. It has far more sustained kind of plateau at the beginning before it drops off. We can see that this actually corresponded to a component 1 score of -0.4. So we could start moving in that direction, or just type it in here. And a component 2 score of +0.02. And so knowing just those numbers, I now am able to accurately recreate the shape that we observed in batch number 2. And so I could go on and on with all of these batches just to demonstrate, but for the sake of time, we won't. Instead, I'll point out that what we have under the hood here is for every single batch. So here's batch 2, which we were just looking at. We have scores on each of these functional principal components that allow us to essentially recreate the shape that we observed. And now we can use these scores in all kinds of different ways to better understand what's driving the difference between these curves and relate their shapes to other variables. So that's just a high level idea about what we're doing when we do this kind of analysis. So now what I want to do is through perhaps a more real world example, actually give you some advice about how to use Functional Data Explorer. I mean, both actually using the platform, so doing what I just did and doing it right, but then also more conceptually, well, what are the other things that I can really use this type of analysis to do? What's the value that it provides? So let's move on.
I also have another question.
Sure.
Is it possible to obtain the equation for that average curve? I know you're showing it visually with that profiler, but can you see the equation?
Oh, excuse me, just had to cough there for a second. So the equation for that curve would be relatively complex because it's, excuse me, I took a quick sip of water and it went down the wrong pipe. With these basis function expansion models, it's essentially a series of weights on a bunch of functions that can take a different form. So they can be step or linear or quadratic or cubic. The equation that would recreate that would not be as meaningful to you, let's say, as the equation for a nonlinear model that maybe some of you are used to fitting, where you might actually be able to directly interpret some of the parameters of that equation. So you can actually basically recreate it using some of the outputs from Functional Data Explorer, but it's not going to be particularly useful or interpretable to you in that form. And so as we go through, I can actually very briefly show you a little bit more about what I mean there, though I don't want to get too deep into the weeds. Were there any other questions that have come in?
Yes, the other one was, can we either see or construct a confidence interval around any of those curves? we'll see a little margin of error in those estimates.
Yeah, so I'm going to say not that I'm aware of, though that could be a gap in my own knowledge about how some of these models work. So if that's something that's particularly important to whoever asked that question, I'm happy to follow up after the fact to get you some more information.
You know, Russ, we actually have Bill Worley is
Oh,
watching too, and he answered that. He said not yet, but it's something we're aware of, and so it's certainly in the queue in product development.
got it. Great. And everyone, Bill Worley, who just answered that question, it's particularly expert in this area as well. Glad that he's in the chat, hanging out and answering some questions. Thanks for coming, Bill. Okay, so are we good? Is the Q&A clean, Kevin? Can we continue?
Yep.
Okay, great. So let's actually take a look at how to use Functional Data Explorer through an example that we saw briefly in the slides, where we actually had spectral data from gasoline, and we also had the octane rating of each gasoline. So here are those data. So what we have here is across a number of different samples, in fact, 60 samples altogether of gasoline, we have reflectance measures across various wavelengths in the near infrared spectrum, so 900 to 1700 nanometers. We're going to go ahead and see how curve shape actually is related to the octane of the gasoline here. So let's take a look at the data to get an idea of what I mean. So here's a plot of all 60 of our samples, and we can see reflectance on the Y, wavelength on the X. And I've actually colored these by the octane, where darker colors indicate a higher octane gasoline. And we can start to see some patterns. I'm actually going to use the crosshairs to zoom in a little bit to show, for example, if we look at this first peak in reflectance at around 1,150 nanometers, we can see that the colors seem to get maybe a little darker as we get higher into this peak. And if we go maybe to the next peak, perhaps we start to see a difference here where we actually have higher octane at these lower peaks. Maybe something like that here, at least in the middle is where we're starting to see these lighter colors. So what I'm basically doing right now is a visual landmark analysis. I'm just cherry picking some peaks, but just to show you that there do seem to be some ways in which the curve shape relates to the octane. And our hope is to use all of the data that we have in a principled way in order to actually uncover that. And so where I'm going with this is an exploratory analysis. We're going to get to some modeling in a bit. But here's the result of the analysis we're about to do. What I've done is actually assigned each one of these samples to one of 5 clusters based on the shape of these curves of these spectra. So for example, here we have samples 1 and 2 and 4 and so forth in cluster 1. And what we can do is actually look for differences in the average spectra on these clusters. So for example, just one that might pop out pretty immediately here is that we have in orange here, this 5th cluster seems to have towards the high wavelength end of the spectra, has a particularly lower peak than the other 4. And so how does all this relate to octane? Well, we can take a look at that too. So here I've actually just created a graph of the 5 different clusters or groupings of spectra that I've found. And we can see that, well, it looks like cluster 2 and cluster 4 seem to have higher octane than the other clusters. So let's see what maybe makes those special. So let's select cluster 2 and cluster 4 and then zoom back in. Okay, well, if we just cherry pick some peaks again, we can at least see as we start to get near the peak, these are basically bookending this first peak where we have cluster 4 at the high end and cluster 2 at the low end. However, they seem to cross over and exhibit a different pattern by the time we get to this peak that is sustained until we get to the 3rd peak and is sustained a fair bit until eventually it crosses over again. And then finally, all the way at this final peak, we see them patterning together. And so this just is a purely exploratory analysis where we start to get an idea about what features of this curve might correspond to higher or lower octane ratings. So let's actually see how I got here. And in doing so, talk about how to use this Functional Data Explorer tool in some detail. So First off, we need to get our data in. So you saw in the first example, we would go to Specialized Modeling, Functional Data Explorer. You're going to notice actually we have 3 tabs here, and this is because there are multiple data formats that are supported because your data might come to you in different ways. So we are dealing with what we would call stacked data, which is one of the 3 types of formats that are supported. So stacked data is just one row per measurement. So I know what sample, what wavelength, and what the resistance was. And so each curve is actually represented across numerous rows here. And we saw before that we could then just specify that reflectance is our y, wavelength is our x, that defines our functions. And then we say, well, sample ID will tell you which row belongs to which curve. But our data might come to us in other ways. For example, here row-wise functions. So row number 1 corresponds to sample number 1. And this column is for the reflectance at 900 nanometers, 902, 904, and so forth. And so we can take those data in as well if your data come to you in that format. You just choose rows as functions and then drop all of those columns into the Y output role. And then if you wanted to bring the sample ID along to label these, you could. Finally, your data might come to you in column-wise format. So here we have one column that specifies the wavelength and then one column for each sample's reflectance values. So here's sample 1, sample 2, and so forth. So if you have data that looks like this, you want to use columns as functions, where you would just put all of your samples into the Y output role, and then go ahead and put whatever your domain or input variable is into the X input role. Now, I want to highlight that when we're looking at these rows and columns as functions, we're dealing with a particular type of data. This is known as dense data, so it's evenly spaced, and we have the same number of observations per curve. So when I say evenly spaced, I mean in our domain. So it's every 2 nanometers here, we have a measure. And that's the same for every single sample that we had. Your data don't necessarily have to be dense, so evenly spaced with the same number of observations. They can be sparse. So if you're measuring things over time and you don't have a consistent measurement schedule, so maybe your data aren't spaced evenly, some curves have more observations than others, that's totally fine. Functional Data Explorer can handle both dense and sparse data. We have some nice dense data here. So let's stick with it. Oh, sorry about that, everybody. Just froze up on me for a second, but we're back. All right. So we'll launch Functional Data Explorer. We're going to stick with the stacked data format. We've done this a couple times already. So now that I have it set up and I click OK, we get the control window that we saw before. And I skipped over basically everything in this just to boost your intuition for what the tool does. Now we're actually going to talk about what all of these different features do and when you would actually want to use them, so that if you want to start using this on your own data, you feel like you have the baseline of knowledge to do so.
Hey, Ross.
Yeah.
As you're going through this example, can you show how you're selecting the number of these functional components? Because obviously this is very similar to principal component analysis, right? Where you look at the percentage of variation the components are explaining. Can you show where that output is that helps you make that decision?
Yes, we will be going over all of that right now.
Perfect, thanks.
Yep. Okay. So first off, what are we looking at? I already mentioned what we have here is just a plot of all of our data. So these are all the spectra, all 60 of them overlaid on a single plot. And then down below, we have the individual spectra. It's just showing us the first 20 by default, but I could pull up additional ones as well. Down below, we have a basic summary of our data. This just helps us get an idea of what data we have and where some of the variability in our curves are that we might ultimately try to model. So I have just over 24,000 total observations across 60 functions, and I have below that the mean, min, max, and standard deviation of all my values. Here's what the mean spectra looks like. So at every single wavelength, what is the mean value that I observed? And perhaps importantly, next to that, I actually have the standard deviation at each wavelength. So this gives us an idea of where the variability in our curves are. So for example, in these lower wavelengths right here, we can see the variability is relatively low. That actually corresponds to this part of the curve here, where you can see there's some variability, but not a ton. The points seem to be pretty tightly packed. Whereas, let's say over here towards the end of our curve, we can see a big spike in variability. Well, that corresponds to this part here, as we can see the variability is relatively tight. And once we hit this little shoulder here, the data starts to spread out quite a bit. And certainly it's very prominent to us right at the end, near the top end of our spectra at 1700 nanometers. So the standard deviation plot just lets us know where the variability that we might try to model actually is across our domain. Now, when we get data in, or at least when I did before, I went straight to modeling, but you don't always want to do that. Depending on the type of data that we're dealing with and how clean they are, how well they were measured, we may need to engage in some data pre-processing, which is what all of this stuff is right here. The whole idea in data pre-processing is basically to improve your signal to noise ratio. What you're looking for are the meaningful ways in which curve shapes vary, and you might need to essentially do some pre-processing on your data to help the analysis pick up on that. So you have a few options here. The cleanup options at the top, it's all about just filtering data or maybe removing data as necessary. For example, if you're working with sensor data, you might get a stuck sensor that continues to read the same value or maybe returns an error value when it's not functioning properly. So you might go to, let's say, remove value and remove that error code from your data before continuing. Or for us, maybe I actually want to look at just a subset of the total spectra that I have here. So instead of the full, 900 to 1700 nanometers, I might instead look at, let's just say 1200 to 1500 nanometers. And so these are the curves that I would be analyzing instead of the full ones. Now you can see right next door, we've actually added that cleanup step to all of our data pre-processing steps. So we can help keep track of what we've done, or maybe even remove something if it turns out we don't want to do it. In the transform section, this is where you perform, as the name suggests, data transformations. For example, a log transformation, or maybe standardizing. For example, you might want to standardize your data because it's really, how many standard deviations away from the mean is a value. It's not its absolute value of the measurement that matters. And then finally, in the align section, this is all about actually realigning observations in or across that input domain. This can become particularly important with temporal alignment of your curves here. For example, I might want to, instead of aligning by wavelength, I might want to just align these according to wherever their minimum reflectance value was observed. So if I click align minimum and now look over to the left before I release this button to the main graph, you'll notice that the X changes from wavelength to aligned wavelength. And what we have here is the 0 point. So this represents the point at which each wavelength or each curve was at its minimum reflectance value. And so it's shifted all of the curves slightly. This might be useful if what I really think is important here is somehow relative to that minimum value. Maybe it's the drop or rise out of that minimum value, for example. Any of these cleanup steps might be a way for us to just improve our signal to noise ratio. And so you want to make sure to engage in some of this data pre-processing, especially if you're not getting what you think are sensible results. So after this, we'd want to fit some curves to our data in order to then be able to extract the shape features. We have a number of different options. The most common are what we'd call the B-spline and P-spline models. You're going to find these model choices up here. So as it says, these are for non-periodic, so non-oscillatory data. In the initial example, I chose B-splines. So let's just choose the B-spline models. What has happened is we have fit these basis function expansion models, or B-spline models, to our data. And that's represented by these red curves that we see. We need these in order to be able to extract the shape components, but what we want to first do is make sure that this spline model that we fit to all of our curves is actually a good one. And so here's how we select models. Off the bat, for whichever one we've chosen, B-Spline, P-Spline, or others, the tool is going to automatically select the best form of the model for us. So by form, I'm referring to this information right here. So the number of knots in the spline, which also corresponds to all of these points along here, and then the degree of the spline. So that refers to these right here. So whether we're dealing with linear, quadratic, or cubic splines. Now, for those of you not familiar with these types of models, you might be saying, well, what the heck does that mean? The beauty of this is that you don't honestly have to know a whole lot to be able to use it effectively, because what we need to do is, through a combination of exploring the model fit and using some diagnostic plots, just make sure we have a good model. Up here,
Also,
we actually, yes?
oh, sorry, Ross, I cut you off. A question came in about how do you know that you've minimized that signal to noise ratio that these curves are doing that? Is there a piece of output you look at to see?
That's kind of, as far as the data pre-processing goes, I think that's where science meets art a little bit, because when I say signal, what I really mean are the true underlying shape features that are important, that are the things we need to capture. And those, by definition, are unknown. And that's what we're trying to get to here. Now, we might know some main sources of noise, for example, like error codes. We want to get rid of those. But in other cases, because we don't really know what the true signal is, I don't know exactly how one would go about quantifying that. But if that's something probably worth talking about a little bit further for whoever asked that question, so we could maybe do some follow-up. Okay. So what JMP has done is chosen the best model for us. That's represented in this plot up on the right, where we've essentially minimized a certain fit statistic called the BIC. And it's found that a 20-knot third-degree model is the best one. Now, I can use this plot and also the knots that are displayed up here to try different models. So for example, we've fit numerous models with different numbers of knots. And so I'm going to go ahead and slide down just to show you what maybe a simpler model looks like. So here's what a 9-knot third-degree model would look like. And so look at this red line right here. So you might be looking at that red line saying, well, what I'm trying to do is accurately capture the data. And that just looks, pretty bad, right? We have a little bump in the curvature here that clearly isn't following the data. Then we rise up kind of poorly through this initial hook. We miss that peak, dramatically underfit that peak, and so forth. And so obviously this is not a particularly good model of our data. So odds are we probably want to stick, at least initially, with the one that JMP has chosen for us. But if you'll notice, if I just do what we just did, this model doesn't appear to be so hot either. In fact, it's still kind of missing the fact that we have a little peak and then a drop and then another increase. And so it could be the case that the B-Spline model here is just not the appropriate one for you. So you might try some other models. So we have P-Spline models. These stand for penalized spline models. They're particularly good for helping to prevent overfitting if you have a model that essentially just follows the data way too tightly, including all of the noise. We have models for the oscillatory data, so that'd be the Fourier basis. So we also have something called direct Fpca. So this basically skips the whole modeling step together. So what I could do here is, instead of choosing any of these, if I go to direct functional Pca, we can essentially perform the rest of the analysis and getting these shape components without fitting pre-specified models beforehand. Now, this does involve some trade-offs. We actually basically align the data in our domain from 0 to 1, just like we would if we were engaging in that same pre-processing step. And if we have some missing values at particular points along the domain, we actually have to interpolate them. So there are some trade-offs there, but if it's reasonable in your domain, you can actually skip the modeling step and go straight to extracting these shape components. So I would like to talk about that in a little more detail here. So here we can see we've landed on 5 shape components. Now, how did JMP do that? Well, it actually used this fit statistic that just popped up before, the BIC, in order to choose the appropriate number. But we can use this interactive slider in order to change the number of components. So here we have 4 or 3 or 2, and all we're really doing so far is just actually dropping off these graphs and removing them from our table on the right. Now, ultimately, we're going to be using these scores to do something, and we would be specifying in this case that we only want to use 2 functional principal component scores. Might actually leave it in this case at 5, given that we have better performance as shown in both this graph and then also in the eigenvalues report. So this shows us the % of variability accounted for by each of these shape components. So for example, eigenfunction 1 right here accounts for 78.1% of the variability in our data. Eigenfunction 2 accounts for 12% for a cumulative total across 1 and 2 of 90%. Eigenfunction 3 accounts for just under 7% for cumulative just under 97%, and so forth. And so you can use a combination of our fit statistic here and these eigenvalues to choose the right number of components here, because ultimately you want to be able to capture the data as accurately as you can. Now we've already seen, if I scroll down, that the next place to go is this profiler, which will actually help you understand how changes in the scores for these different shape components actually affects the overall curve shape. So once your modeling is done, one of the first things you want to do is just get down to this profiler and actually see what changing these values does to your curve shape. So I'm going to get rid of the score plot here. And I don't think I'm going to be able to quite fit it all on one. No, let's see. Yeah, here we go. So let's say I want to know, all right, that's a pretty complex shape. It's hard for me to map that onto differences in these curve shapes. So what I'm going to do is actually just change the values and see on the left what happens when it's low versus when it's high. And so I can see those 2 intermediate peaks when this is lower seem to get larger. When I go to the right, they get smaller, but that final peak starts to get more pronounced. And so that seems to be the main variability that this particular shape component is capturing. And so I might go down the list here and use the profiler to explore these other shape features as well. This one seems to be playing mostly with that final peak, making it more or less pronounced. And so here I can use this to actually understand the primary ways that these spectra differ in their shapes. Or if I go to my function summaries, I now have for every spectra that we collected, all 60 here, I have their scores along each of these functional principal components and some additional measures as well. So if I wanted to use these, like I did for that clustering example we started with, I could click the red triangle, go to Save Summaries, and now I have these values for further analysis. So here are the 5 FPC scores right here. So I might submit these to, let's say, a hierarchical clustering. Choose whatever solution I want. Typically in this, we're looking for a notch. Oh, struggling to select 5. That's all right. We will just do it the old-fashioned way. So we can see here in our distance plot, we're kind of looking for an inflection point, and 5 seems to make a good one. So let me save these clusters to our data table. And now I've essentially created groupings of our 5 spectra that, as I showed at the beginning, can be used to actually just graph the clusters to look for different profiles or to figure out how those clusters correspond to different octane ratings. This is just all purely exploratory in this case, a way of looking at the different shapes of these spectra and how they might relate to some external variable that we care about. So what I'd like to do with the little bit of time we have left is just boost your intuition for some additional uses of functional data analysis through a couple other examples. And so we're not going to bother clicking through everything to see how I did all of this. This is really just to help give you a better idea of some of the things that you can actually do with functional data analysis beyond the exploratory analyses that we've done thus far. Let's imagine a situation in which we are milling pigment for producing LCD screens. Okay, so in this case, if you're doing this for research, maybe you're trying to optimize some new process for creating a new technology. Here I have a data set where we collected size over time measurements in a milling process for these pigment particles. And here's what they look like. So you can imagine a situation in which we turn on a milling device. In this case, it's a bead mill. And as we run it, the size of the pigment particles that we start with get smaller and smaller and smaller until ideally it drops into this green range that we would consider optimal. And you can see across different runs of our milling device, we sometimes get into that green range, sometimes we don't. Sometimes we get there pretty quickly, which is great. Other times it takes us a while to get there. And so I might want to understand better how certain factors, so here are 4 factors that I could control regarding the milling process, how they might be able to get us to a desirable curve shape, which is actually depicted down here. Wouldn't it be nice if I could achieve a curve shape such that I turn on this milling device, we drop almost immediately into the desirable range. Oop, wrong button there, apologies. And then we just hold steady there. Now, the trick here is that we don't want to over mill our particles and end up with particles that are too small if we happen to leave the mill running for too long. So we can use functional data analysis to actually figure out how to optimize a curve shape. So what factor settings across these 4 factors will get us as close to this target as possible. Now, I'm not going to get into detail on it, but you can use designed experiments to do this. And the data here actually from a designed experiment. If you design an experiment in JMP, you have the option to declare a functional response type. So in this case, it would be size over time as the response in our experiment. And then you could specify all the factors that you might use in order to modify that curve shape, our 4 factors here. For the sake of time, I'm not going to bother designing the experiment right now. We're going to get to the analysis. So if I go to Functional Data Explorer, I would put time in my X, size in my Y. Here are the different batches or runs of my milling process. And then what I'm going to do is take our 4 factors and put them in as supplementary variables, which is going to enable something pretty great here. Now, first off, I would engage in any data cleanup I have to do. You may have noticed previously this load target functions option on the right that I didn't mention. This is for a situation just like this where you actually have a particular curve shape that you're trying to achieve. So I'm going to click load and just tell JMP that the one labeled target in the gold dots there is actually not real data. It's just my target curve. I'll proceed with the analysis as usual. I'm not going to go through all the ways of looking at whether or not our model's good. I declare a B-spline model. I get 1 shape component out. Normally, I would explore that a little more, but what I'm going to do next is request a functional DOE analysis. What this is going to do is create a model that uses our inputs, so those milling factors, and predicts the shape component score, that Fpca score, and then allow us to see how changing our factors affects curve shape. So here I have a profiler that lets me do exactly that. Here is the predicted curve shape based on the value of the 4 factors that I put in. And as I change them, I can actually see how curve shape changes. So we can see with a low % beads, we have a steep drop off followed by a shallower drop off that continues through the end of the time. Whereas as I go higher, we start to get a steeper initial drop off and it starts to level near the end. So I can actually use this now to figure out how I should set these factors in order to achieve the desired curve shape. So I'll just ask JMP to figure that out for me. And it shows us that, well, if I have the maximum value of percent beads and percent strength, the minimum value of flow and the maximum temperature, I would predict that I would achieve a curve shape that looks like this, which is starting to get towards that optimal one, though actually the drop off here is not as steep as we might want. We wanted something kind of like this. And so right here, we're actually capturing the fact that it's in that part of the curve where we still failed to hit that target. So this is functional DOE analysis. As you can see, this is something that's actually just built right into the functional data analysis Explorer platform. It actually calls out to generalized regression in JMP Pro in order to do that. If you want to talk more about the approach to functional DOE and how it all works, I would be happy to do that on follow-up. But for the sake of time, we'll show one more example just to boost your intuition for the kinds of things you can do with this analysis. And to do that, we're going to consider a situation where we might want to use curve shapes as model inputs. This is in a fermentation process in a biomedical setting. So we have cells actually producing some kind of compound or enzyme of medical value for us. So what I have here is a number of fermentation batches. And over time, I've measured a number of different things. So the ethanol level, the temperature, the feed of molasses and NH3, and so forth. So what I really have are numerous curves that I might want to model and ultimately figure out what the ideal shape of each of these curves would be in order to optimize some other measure. So for example, the yield of this fermentation process, which I have a yield measure for each batch right here. Now, I'm not going to, just because we have a couple minutes left, get through all of the analysis here, but suffice it to say, in some situations, what you want to do is actually run an analysis or a functional data analysis on numerous different curves together. So here I have an analysis done on ethanol, where I've uncovered, in this case, 8 different shape components, though perhaps starting to wonder maybe if I start to see oscillations like that in these components, if it's real or if maybe we're starting to fit to noise. And I've done the same for all of these additional components here. Now I can, if I want, save all of the component scores for all of these different curves out to a single table. So here are the scores for ethanol. Here are the scores for temperature and so forth. And now what I've actually done is create a model that allows me to change all of the values of these FPC scores and see how it affects yield. So here's our predicted yield, just represented as a straight line representing the level of yield in this panel. And here are all of the curve shapes for all of these functional inputs. So if I achieve curve shapes that look roughly like this, I would expect a yield of about a little over 53%. I can see right here that it looks like ethanol FPC2 has a particularly strong effect on yield. Okay, in fact, if we look at the shape of the ethanol curve, if the curve looks more like this, I expect lower yield. In fact, you can see on the left, that's about 0.485, 48.5%. But if the ethanol curve looks more like this, with an initial peak and then stabilizing down at a low level, we would expect yield at over 58%. Maybe next I notice this seems to have a big effect on yield. This is the molasses feed FPC4. So if we look at yield and then the molasses feed curve, looks like a molasses feed curve like this results in a lower yield than a molasses feed curve that looks more like this. And so you can see I have numerous curve inputs. They have complex shapes, but with functional data analysis, I'm able to actually determine what the shape of each curve should look like to achieve the outcome that I desire. And so, of course, there's a bit more. I didn't click through all of that analysis. This is just to boost your intuition for the kinds of things that you can do. And again, this is something that we'd be happy to follow up with you if you really do have a strong use case for this, to help you actually learn how to do this in your own situation. So we're just about at time. I'm going to throw open one more poll. And as I do, Kevin, I'll ask you to maybe feed any questions that we have remaining as we wrap up here today.
Let's see, I think we just have one more. Let's see, did that, and I know you're going through the examples really quickly at the end here, just so people can see different applications, but the question was, did the functional DOE actually help in reaching the target curve?
Yes, in functional DOE analysis, we did find a group of factor settings that got us as close as feasible to that target curve. We didn't hit it dead on, but it might not be physically possible. In fact, I mean, the way I structured that curve, it was basically that you turn on the milling device and instantaneously you are at the desired particle size, which of course isn't physically possible. But we got as close as we could, or at least as we know we can, given the data that we have.
Okay, I think that actually wraps up all of the questions.
Okay, great. Well, we appreciate everybody coming out today. I see a number of people answering this final poll question before we go. We recognize that this is a more advanced or more challenging topic, but it's also the techniques we've been looking at today are ones that can provide an extraordinary amount of value if what you deal with is functional data. So again, just know that the JMP team is here to actually help you implement this stuff so that you don't have to figure it out yourself. So either hit yes on the poll or email us at academic@jmp.com to get that help if you want it. All right, I think that's it.
Ross, this was a great coverage of the topic. I learned quite a bit here, and thanks for showing all those different applications, because I think that's going to help faculty see how they can incorporate it into their class.
All right, great. Well, everybody, I appreciate your time today. Kevin, I appreciate your expert hosting as usual. Please keep an eye out at jmp.com/academic-webinars coming up for webinars beginning in the summer and then again in the fall. All right. Well, take care, everybody. We'll see you next time.